Dear colleagues, to your attention, report on the topic Optimization of the Combined Explosion Hardening Processes by Viktor Shchetynin, Roman Arhat, Vladimir Drahobetskyi, Vyacheslav Puzyr, and Dmitriy Maloshtan. The purpose of these studies is to develop a universal analytical method for calculating the optimal parameters of the process of increasing the wear resistance and durability of parts using pulsed energy sources. This research examines the processes of increasing the wear resistance of mining equipment parts using pulsed energy sources. These processes include explosive cladding with wear-resistant materials, explosion hardening, explosion thermal hardening, and frictional hardening. The result for increasing the wear resistance of mining equipment parts is optimization of parameters, power and thermal intensification of these processes, development of fundamentally new methods and technologies of hardening. In addition, the search for technologies for restoring the wear resistance of parts without dismantling them is also promising. The factors or parameters of the research processes. The main parameters of explosion welding, such as kinematic and physical, include speed of movement of the point of contact, nu-c, dynamic impact angle beta, plate driving speed nu-0, pressure, impact duration, temperature in the impact zone. The technological parameters are following. Detonation velocity d, which characterizes the type of explosive charge. Dimensionless welding parameter r, the ratio of the mass of the explosive to the mass of the driver, such as plate or pipe. Distance between the welded workpieces, welding gap h. The factors affecting the degree of the explosive hardening include the applied pressure, the duration of the impact pulse, the nature of the loading, and the velocity of the linear pulse. For explosive friction hardening, the factors are the same as for explosion hardening, only instead of the linear impulse velocity, the velocity of the friction material is used. The physical and mechanical characteristics of the processed material affect the efficiency of the explosion welding process and the degree of hardening. The processes of explosion welding, hardening by convergent shock waves, a layer-on charge of explosives, proceed under the action of one type of external load. The rest of the processes occur under the action of several independent or dependent loads. From the specific conditions of deformation hardening, functions from F1, F2 till Fn are determined by one of the types of load. When the process takes place under the influence of several independent external loads, n, which are greater than 1, function fq must be determined from additional conditions. To determine function fq for the processes under consideration, the equality of the intensity of deformations is extremely uniform at the minimum total power of deformation. The steps are as follows. First one, the process is subdivided into two simple processes: explosive lowering and frictional interaction of the technological friction sliding pad with the workpiece. Explosive lowering by applying shock wave of the pad workpiece system results in the occurrence of a stressed triaxial uneven compression and driving of the technological pad. Contact friction stresses act on the contact surface of the workpiece with the tool. Second one, determining a functional link Fi as a function of PQ. Third one, in accordance with the equation 2, the functions Fq are determined. In this case, it is considered that P1 and P2 are not independent, but may influence each other. Here, P1 affects the speed of movement of the technological pad and the force of normal pressure between the pad and the workpiece. Fourth one, determining the relation between factors P1 and P2 from the condition of the minimum deformation energy when the deformations of the hardening surface are limited to the limit uniform 1. A method based on the decomposition of a combined process into simple ones and subsequent synthesis makes it possible to optimize the processes under consideration. The mutual influence of factors is assessed by the sum of the terms containing the partial derivatives of the function and the corresponding points. At the same time, we represent elementary processes as a set of even simple processes. The approach to regarding problems of this class means that the problem of finding the optimal loading parameters is solved by numerical methods of nonlinear programming. To maximize wear resistance under conditions of shock abrasive wear, it is necessary to minimize the mass wear, U. To reduce wear, it is necessary to reduce the value of the coefficient of friction, increase the hardness of the material, the temporary resistance to fracture, and the relative elongation of the material of the part. The minimum value of the coefficient of friction is reached at a certain value when sigma n is equal to sigma 0 n. Its value is largely determined by the operating conditions and the geometry of the part. The relation has no extremum by sigma b and delta. However, if the numerator and denominator in the equation 6 are divided by sigma n, in the denominator we come to expression of multiplication of epsilon to delta, where epsilon is portion obtained by the division of sigma b to sigma n. Since sigma b is greater than sigma n, then epsilon is greater than 1. At the same time, the division of hm to ha is less than 1. The multiplication of epsilon to the division of hm to ha is equal to lambda, and it is less than 1, and the sum determined by statistical data, lambda plus delta, is constant. In this case, product multiplication of delta and lambda provided by the equation 5 will be maximal when lambda is almost equal to delta. For hardened head-filled steel, when rubbing against granite with an interlayer of iron oxides, lambda is almost equal to delta and almost equal to 0.4. When rubbing against manganese, lambda is almost equal to delta, and both are almost equal to 0.7. The proposed method for calculating the loading parameters of combined and multi-stage deformation processes makes it possible to simplify the calculation of the parameters of the hardening process and reduce the calculation time by methods involving the use of nonlinear programming methods. The transformation of the wear dependence by mass enabled the determination of rational parameters of the plasticity of the part depending on the ratio of the hardness of the abrasive and the surface of the part and the ratio of the normal pressure of the abrasive and the strength of the material of the part. In conclusion, it should be noted that the considered technologies can be successfully used to strengthen the elements of railway tracks, tracked vehicles, in loading and unloading equipment. Thank you for your attention.